and and conducting spherical charges. So anything that's spherical or a point charge. But I want to be very careful. I'm saying a point charge. If you have multiple point charges, Gauss's law can't work for that. Because when you have multiple point charges, the electric field is no longer symmetrical. So you have to understand, when I say we're exploiting the symmetry, we are exploiting the symmetry of the electrical field. So 1 point charge has a symmetrical electric field. 2 point charges in space do not. Right? The field is disrupted and curved in ways that are not easily predictable. We need to be able to draw or have an understanding of what the electric field will look like. We do around spherical point charges that are isolated in space. And I think you could probably also imagine a spherical insulator would have a similar property. It would create what looks like a point charge, just that it's a sphere, not just a single point in space. The second kind of situation that works great is the infinite line of charge. And we'll talk a little bit about that one today, the infinite line of charge. And the third one, infinite sheet of charge. An infinite sheet or infinite plane, if you like the mathematical term better. Now, can you guys even see? Am I blocking you? I look like you're some crap.
I know.
You're okay?
Yeah. It's not you, it's
So Tuesday we'll break out the computers and I'll put the codes up and you guys can have whatever. All right? So that'll work better. You know, I've looked at where I was going with this. I know we're going to say the word infinite a lot, but I want to bring you back to something we did last week. Do you remember when we had and talked about a bar of charge? And we did some Coulomb's law work to figure out the force from a bar of charge. Do you remember that conversation? And we came up with some ridiculous thing that I was really waiting for the overzealous kid to go home and do the antiderivative of what we came up with, but nobody did. Don't worry, I'm sure it'll come up again. But when we say infinite line of charge, and my example started with a finite bar, we were trying to figure out, well, what would be the force on a point charge that was here? Today I would say what would be the electric field at a point at the middle of the bar, maybe a distance z away from the bar. In this class, when can we treat the bar like it's an infinitely long bar? So if you look back at our calculation for this, you'll notice that we had limits of integration that limited us to the length of the bar. But if it goes on to infinity, you find that in trig terms a lot, that means you get a sine or a cosine that works out to be 0, which kind of helps out because if you figure this line right here, where this angle was important. Well, what happens when this piece goes to infinity? Do you see how that angle goes to 90 degrees? And there's always a trig function where the cosine or sine is going to give you a 0, right? So a lot of times, wondering if you can treat your object as if it's infinite gives you a lot of latitude to assume it's infinite when even though it's not. So like it becomes more and more infinite the closer we get to the bar, right? Because the closer we get to the bar, the more that angle approaches 90 degrees. So the bar doesn't have to be an infinite line of charge. We just have to be kind of close to the bar for it to appear that way. Do you guys understand what I'm trying to say? That's going to be true for a lot of what we do in here. What it does is it produces what are known as edge effects, where as long as you're in the middle of something and you're close to it, your object appears to be infinite. Only when you start getting towards the edge of the object does the symmetry break down. And we'll refer to that as edge effects. A lot of the things that we will create in here, capacitors being the first one, will be of finite size. They will be something that is finite in the room, but we will base their properties on the idea that we've made some assumptions that we are close enough to them or they are big enough relative to the size of the device that we can treat them as though they are infinite. And I'm spending this time talking about infinity because nothing, of course, there is no infinite line of charge. There is no infinite sheet of charge. But if I have a sheet of paper and I say that we're going to talk about the electric field from a charged sheet of paper. And by the way, this is not just some fake discussion. That's how a laser printer works. A laser printer charges the piece of paper electrically, and the toner is attracted to the electrical part of the page. So the laser that scans that's in the laser printer, where the laser touches, electrically charges the paper from the drum. The laser scans a drum, makes electrons appear on the drum where the laser touches it. That drum touches the paper and then sends it towards the toner. The toner is pulled to the paper because it's electrically the opposite charge. And then it goes into a heat fuser, which fuses the toner onto the paper. That's how a laser printer works. Can you treat the piece of paper as an infinite sheet of charge? Because you want to know what is the electric field around the paper. And they do. The calculation on a laser printer allows them to treat it as if it's an infinite sheet of charge because the toner particles are so small compared to the piece of paper. So compared to the toner particle, the paper looks like it's infinitely big. Does everybody understand how we're going to use the idea of infinity? I mean, an electron is incredibly small. So a piece of paper is infinity if you're an electron. So when we talk about what does infinity mean, you just have to recognize that infinity isn't as far away. In fact, the infinity symbol is written on the wall over there because I was unable to drill that into people a couple of years ago. And I just wrote, I go, look, infinity's on the wall. Why? Because it's not that far away. If you're small enough, a lot of things look infinitely big. What?
Where's the infinity?
Do you see where the Haunted Mansion painting is? It's to the left of it next to the bookshelf. You can't see it from your seat. It's blocked. I can't see it from where I'm standing. There it is. That is the actual right statement. If you can't see it, it's infinitely far away. All right, so hear me out. Couple steps. Step number one, as we talked about yesterday, is that we have to let's just do this problem. I don't want to make it more. Let's say we have an infinite line of charge. So something that is super, super long compared to like I said, I can't tell you how much charge it has. It's infinitely long. So it has a charge density of lambda. If you'll remember, that is charge per unit length. Now, before we start a Gauss's law problem like this, we should take a few seconds and maybe using our imaginations, figure out what the electric field probably looks like around an infinite line of charge. First, there's this 2D projection, what we would see by looking at it like this. Can you imagine that if it's positive charge density lambda, that the electric field is probably going away from it like that? And because it's in a straight line, can we also probably realize that the electric field probably has a certain uniformity to it? Do you see why I'm saying that? I'm just using common sense, but it's not always particularly common. But can we also recognize that if I was to somehow look down the length of this infinitely long line of charge, that the electric field probably looks kind of like this if I'm looking down the length of the wire. Would you guys agree with that too? So we want to exploit this symmetry, but the first thing I want to do is figure out, well, what's the exploitable parts? What parts of my field have symmetry that I can exploit. So I'm kind of getting an idea that I have certain amounts of this field that have some uniformity, where I will probably be able to say with reasonable certainty that the electric field this far away from the line is probably the same value as the electric field this far away from the line. Is that, I think, a reasonable assumption? And similarly, looking down the wire itself, I would have a symmetry that the electric field here, maybe even the electric field in a circle around the wire, would be the same all the way around the wire. You guys think that that's okay? So, I'm trying to figure out the symmetry of the wire, because I want to come up with a shape that I can wrap around the wire that I can use to exploit the symmetry. Our goal is to figure out what is the electric field, say, a distance z away from the wire. That's what we're going to try and find out. Remember, we're going to use Gauss's law to come up with an expression for electric field. Now, this part's going to be a little weird because when we did this last time, we wrapped our Gaussian surface around the entire point particle, right? The rules don't say that I have to enclose the entire particle or the entire object. The rules simply state that the electric flux will be equal to the amount of charge enclosed. So I'm not even going to bother to try and wrap something around an infinitely long wire because by definition it is infinitely long. All I need to do is try and trap a certain amount of charge inside my Gaussian surface. So I'm thinking I'm going to use a cylinder as a surface that I think will work. When I say cylinder, I mean it's just how it sounds. I'm going to use a right regular cylinder that I will wrap around my infinite line. Like so. I'm going to try and center the cylinder so that the edges of the cylinder, the round part of the can, are all the same distance away from the line. So I want to center it so this entire thing is a distance z away from the line. Basically, z is going to be the radius of my cylinder. Does that make sense? And I'm also going to recognize that because it's a cylinder, it has a height, h. Remember, my job is really to try and say, can I find a geometry where the electric field is the same amount everywhere along the surface, so it's a constant, or can I find a geometry in which the flux is zero? Those are the two things we talked about yesterday. That's what I'm trying to create. So, first thing, if I look at the flux, just talking about how much flux there is it clear to you that along the circular part of the can, the outer edges of the can, that the electric field will likely be the same size everywhere around the circular outside portion of the can? Yeah. Is it also clear to you that no electric field appears to pass through the top or bottom of the can? Right? If I make the can just right, shouldn't the flux be zero because of the angle of the can relative to the electric field? That's a complicated statement, so let's zoom me in right here. Can you kind of see that the direction of the area of the top has to be this way because it has to be perpendicular to the surface, and the direction of the electric field at that point is this way because it has to be perpendicular to the line. So the dot product for the top is going to produce zero flux because no flux passes through the top. You guys follow that okay? And can I use that also at the bottom? Yeah. So I don't think there's any flux passing through the top or the bottom of the can. I do, however, believe that the area of the can on the sides is perfectly aligned with the direction of the electric field on the sides. So can we all kind of agree with that statement? Is that okay with all of you? Because this is something that you may not know that you can do. I'm going to kind of get that smaller so I have room. This is a summation. So I don't have to do the summation all at once. If I want, I can do 3 summations. 1 for the top, 1 for the bottom, and 1 for the sides. Note the circle is gone now because each one of these is a partial summation. And this is the summation that will go with the top of the can. This will go with the bottom of the can. And this will go with the sides of the can. I don't know why I wrote a plus in the middle of this one, so let's be better, Mr. Shelton. So you guys who have had calculus do know that you can break an integral into multiple parts and sum all the answers. But if you didn't know that, or if you haven't had calculus yet and you're still, have no idea what calculus is, it's just a summation. And if you'll remember with the summation symbol, how you just have multiple terms that you're adding, well, you're just adding, so I can add them in groups if I want. So it works the same way for an integral. Now, I spent a lot of time developing my surface, but do you realize to do so, I did it by trying to make sure the flux through the top would be 0. This is because I'm going to have the cosine of 90 degrees for the dot product. And the same for the bottom. The flux to the bottom will be 0. And this again is because I'll have the cosine of 90 degrees between the electric field and the direction of the area. Which leaves me only having to worry about the integral for the sides. However, we're in agreement that for every point on the side, I'm going to look right here for this. dA is this way, and the electric field is also this way. Is there any point on the sides where the electric field and the area won't be aligned? So the dot product for every point on the sides is going to be the cosine of 0. Right? We kind of forced it to be this way, and is that okay for all of you? Just make a reasonable sense a little bit? Now, can we also state that the electric field is probably the same amount because we are the same distance away from the line everywhere on the sides? Does that also make sense? If so, then I can rewrite my integral as the integral, E outside, integral of dA for the sides. So I know we're a long way from where we started, but if I'm summing the area for the side of a can, what would that be? Do you know how to find the surface area of a right regular cylinder? There's the top and bottom of a right regular cylinder, and then there's the side, right? We're just going to have to kind of work this out, right? Doesn't it look something like that, those 3 parts? And I don't care about these parts, so this is the one that matters, right? Yeah, it's just base times height, isn't it? So I'll have 2 pi r, that's the circumference of the cylinder, times h, which is the height of the cylinder. Will this be the area of my cylinder? Except I'm not going to use r because we said our cylinder has a radius of z. So this will be 2 pi zh. That is the total flux for my cylinder. That generally is the hardest part of this, is coming up with an expression for the flux. But I'll say this very clearly. Once you've done it once for the infinite line, every infinite line thereafter is the same. They will all look like this. You've done it. The only time that we're going to come back to this and have to do it different is when the line is an insulator and is thick, and we have to look at the electric field inside the wire, which we will do. It's not hard. It's just same application, same process, same shape, same everything. So we will be able to do it. It'll be okay. But we have to do Gauss's law. This is not Gauss's law. Gauss's law has two sides, Q enclosed and the flux. We've just done the flux portion. We now have to figure out how much charge is enclosed. Some students don't get this part, but we've only enclosed a piece of the line, right? That piece. The length of that line is h, the height of the cylinder. And the charge density of the line is lambda, the charge per unit length. So our Q enclosed will just be the length enclosed times lambda. That's the charge enclosed. Right? We didn't enclose the entire line. We enclosed a small snippet of the line. Is that okay? So Q enclosed for us will be H lambda. That's going to equal epsilon naught times E times 2 pi Z H. That's how Gauss's law is supposed to work if you're trying to find the electric field from a symmetrical shape. We can solve this for E pretty easy, right? Do you see first that the H cancels out? That will happen. Parts of your geometry, the unimportant parts, will cancel out. We expect the electric field to be the same all along the wire. So we shouldn't expect it to be different in different locations along the wire. That's why H cancels out. At the same time, Z doesn't cancel out. Why? It's how far away from the wire we are. I would expect Z to be in my answer. But this part might be a little unexpected. When I solve for the electric field, I don't know why I put a 0 there. Don't trust Mr. Shelton. I solve for the electric field. I get first something that has to do with the charge and where I am, right? Lambda and Z. But I also get a collection of constants. 1 over 2 pi epsilon naught.
What's the K, right?
Well, it's like K. I mean, we know K is 1 over 4 pi epsilon naught. So this looks like it is twice as big as K. So you could say that this is 2K. But also, it kind of says the electric field is stronger around a line of charge than a point charge, which I would kind of expect because it's spread out over more distance, right? I would expect it to be more powerful. Now, of course, that all depends on this, but also please notice this. With the point charge, we had Z squared in the denominator, right? The further away we got, its electric field died down by 1 over the distance squared. Obviously, this dies down by just 1 over the distance. So the electric field doesn't taper off as fast near a line of charge as it would a point charge. But I took an entire class period plus a little rant at the beginning to just develop this. It's not accidental. I know I can't do more than one in a class period, but I also know how important it is that you know and understand this. How many of you feel pretty confident that you understand where this came from? I do not expect you to be able to redo it today or tomorrow. I expect through practice that you could redo it. All right.